Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, well, I'm just going to remind you the 3 books that are on sale. Drink tea and read the paper. If you're a green belt and a black belt and you want simple instruction on how to apply your skill, design of experiments for 21st century engineers, and finally, a statistical process control for small batch production. They are all available from lulu.com and the links are in the video below. Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, we're going to take a look at a case study for one of my clients. Hope you enjoy it. Okay, let's get into this case study, which is very much Lean and Six Sigma working. Very much Lean and Six Sigma working together. The ultimate project that you're going to see is about improving the quality of welding. But first of all, we have to find that problem. So there's a certain amount of German on these slides, which I apologize for in advance, but hey, it was a German client. So let's take a look at what's going on. So here's the team. You can see in the background, look, just behind the team here that took part in this work. There is, we're going to get lean here. There is the value stream map. One of my other videos talks about project selection. This is a great example of how to select projects. We were doing some lean work in this company. We did a value stream map in order to find the priority issues in the value stream. One of them turned out to be perfect for Six Sigma. So there's the team. Here's the product. This product, let's have a look. It's about 1 meter wide, this thing. So it's about 1 meter wide. It's an iron core. It's an iron core that is part of power generation equipment. So it goes into a power station. The iron core is part of the large transformer that creates electricity. So you don't want this thing to fall to pieces. And the way that it's made, you have slices of metal here. You can just see them. And then what we do is we weld across the top and across the edges to weld all these pieces together to form the iron core. So that's the product. That's what we're making. As I mentioned, the team, we took, by the way, it took us 4 days to create a big picture map. It seems like a lot, especially for a team of about 10 people, but bear in mind, 4 days, you might do one of these every 3 years. Okay, because once you create one of these things, there is 3 years worth of projects on this map. Now, one of them, look, there's a rework loop. There's the opposing arrows, look. There's a rework loop on this map, so we have a quality problem that's causing havoc in this particular value stream. Let's take a look at the problem. So you can see a little bit better now the slices. Whoops. You can see the slices of metal, and you can see the way that we weld across this way in order to lock them together. Here's the problem, look, the quality of the welding. And you can imagine when you get this problem, the whole piece goes in the bin. I mean, these are big, expensive pieces to be throwing away. So that's our problem. Now, it's a technical problem. So once you get a technical problem, we've been looking at a lean tool, we've been looking at a value stream map, a big picture map, but now we have a technical problem.
And the minute you have a technical problem, well, I'm going to switch toolkits, because suddenly this is a Six Sigma problem. It is a perfect Six Sigma problem. So we're going to form a specific team in order to tackle this problem. And we're going to go through some basic procedures. This slide is sideways, but first thing we want to do, process flow of what goes on. So process flow of the welding procedure. Now, one of the things we need to do before we get this project up and underway, so we're thinking about define and measure in the early parts of the project. The current problem, the current measure look, is the welding looks terrible. That's not really a great measure. We need to find a better measure in order to make the problem easier to understand. Now, talking to the team, I'm not a welding expert, but talking to the team, what they said was, you get these dots of spatter. The dots of spatter are a bad sign. That's bad welding. So the more dots of spatter we get, the worse the weld is going to be. So they're saying the dots of spatter is the indicator of a good weld. So what we're going to do, we are going to count spatter as a measure of success on this particular project. It's a little bit rough and ready. It's not the best measure I've ever come up with, but it's much better than saying pass and fail. So moving on, then we start talking about variables. We start talking about inputs. What inputs are important to the quality of the weld? Well, down here, welding parameters, things like the feed rate, etc., were identified as important. The gas, the mixture of gas and the feed rate of gas was important. The level of oil pollution on the parts. These parts are pressed, so you can see each slice here. This is pressed. They're basically a T-shape, by the way. You can't necessarily see this from what we've looked at so far, but they're basically a T-shape. So we press all these individual plates, then we line them up to create the component, and then we weld 2 welds across the bottom, and we weld here. Okay, so they're pressed, and one of the things that they think is wrong is that they are getting oil, cutting fluid. They're getting oil contamination on the parts, and when they try to weld it, it smokes, and that's what's causing this problem. That's what's causing this problem here. So that's one of the things that they want to test. So, okay, cause and effect, some settings, some problems with oil pollution, things like that, some gas settings, etc. So we end up, look, with how many variables? Let's take a look. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 variables. 9 variables are of interest to us on this particular problem. Now, if you took a very traditional approach to this problem, which is a one-factor test, so in other words, you check the gas type and you do some tests, then you check the tip condition and you do some individual tests. Each time you change one factor at a time. Think about this. We need samples for each test. Now, what I can tell you, if you looked at this properly, if you used a proper sample size calculator, the likelihood is it would tell you to get 30 samples for each of these. Now what did we say we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 threes. You need 270 pieces to do this. That's if you take what's considered to be the professional route, the one factor at a time route. We're not going to take what's considered to be the one factor at a time route, however. We're going to do a designed experiment. And one of the reasons we're going to do a designed experiment is because of all that one factor testing is pointless. Because look at this. Look how many combinations we have. We're going to have 2 gas types, 2 types of tip, 2 types of diffuser. We have, I'm going to just say 5 choices. So the torch gap, we could go 10 to 15 millimeters. Obviously, it could be finer than that. But to be quite honest, I don't think we could measure it that accurately. So we're going to have 5 choices on the torch gap. Then we're going to have, let's have a look. There's 4 for the welding speed. Now, again, this is probably more than this because, you know, the adjustment of the machine probably could go in tenths, but we're just going to go 4 there. So we'll have 4. Then we've got what? 8 for the wire feed. Okay, so 8 here. Then the amps. Well, we got 230 to 255 amps. So there's 25 choices there. Okay. Then there's the liters of gas. There's 5 choices there. Okay, and then finally there's drying times. It can be 0, it can be 1, it can be 2. So there's 3 choices there. So what does that come out to? That comes out to there are 48,000 choices. That's how many ways you could set this machine up. Okay, that's how complicated this problem is. And we could be doing 270 tests. You know, look at those big pieces, these things that are meter long, for Christ's sake. Do you really want to be making 270 of these things and throwing them in the bin and maybe not even finding the answer to the problem? So that's the scale of the problem. So we are not going to approach this in what's known as the common sense way, or indeed the professional way in that sense. One factor at a time is not good enough. It's not fast enough. Here's the power of Six Sigma. What are we going to do? We are going to do a designed experiment. We are going to do a DOE. The DOE, by the way, is going to recommend 12 tests. The DOE is a pattern. It is a pattern that is recommended as the fastest way. It is the fastest way to find out. Okay, it's the fastest way to find out. Out of those 480,000 combinations, we want to find the best one. How do we do it in the shortest possible time? You use a design of experiments. Now let me just show you. This is a different welding problem, but this is also a welding problem. And this engineer used his skill. Okay, so this is a client of mine. I taught them design of experiments, and for some strange reason, the engineer decided to go his own way. This is a picture of a flip chart that we created when we were trying to figure out whether he learned anything or not for all the work he'd put in. Look at all the pieces that he's used. By the way, these are expensive pieces. These are castings. They always tell me that these castings are expensive and they don't want to use too many. But look, He did some tests. He used 14. Then he checked the depth of cut. He did one test. By the way, what do you think of a sample size of 1? Doesn't tell you anything really, does it? But anyway, he did a test. He did 1. He did another test. Didn't tell him anything. He did 1. He did another test. He used 1. Then, well, he's getting a bit smarter now. He used 16 pieces to do a 1-factor test about cleaning. Then he used 8 parts to see if a similar part, but that was slightly different, was any better. He used another 8 parts. Then he changed the processing conditions. He used 140 parts, 140 samples. Okay, then he did 12v12. What's that? That's 24 pieces. Then he did 8v8. And again, what's he doing? He's doing a 1-factor test. Then he does another 1-factor test. He uses another 16 pieces and another one. And finally, 4 pieces at the end. I mean, look at this thing. Add it up. What have we got? 14, 17, 35, 43, 43, 183, 183, 187, 207, 207 plus 32, which is 239, 239, 243, 53, 59, 200. He used 259 pieces. And when we got to the bottom of the analysis that he'd done, what did we decide he'd learned about the process? We decided he'd learned 0 about how to solve this particular problem. This is a pointless way to work. Using your skill can never deal with this. You can never carry this in your head. So what we're going to do is a designed experiment. The designed experiment recommends 12 tests. Yes, just 12. Okay, so each one of these, now it's in German, so each one of these is one of those variables. So, you know, the first one, gas type, tip condition, gas diffuser condition, etc. So that's these things here. It's telling us the test pattern. Here is the measurement. By the way, look at the sample size. We are only going to use 24 pieces to find out what 9 variables are doing to this process. How efficient do you want to be? That's just 3 pieces. It's 3 pieces per dial. It's the most efficient way. It's the fastest way to find out. The measurement is the spatter. So we are counting spatter. Okay, 24 pieces. Once we've done the DOE, we then do a simple graphical analysis that looks like this. Each line represents a variable. If the line is long, the variable has a big signal. So the first one, which is the gas type, has a huge variable in terms of the amount of spatter that we have in the process. Now, using this graph, it's very simple. We want to be lower. Okay, it is a lower the better problem. So where are we going to be? We want to be at this end, which is telling us to use this gas. We want to be here. We want to be here. We want to be at 15 on this one. We want to be at 12 on this one. We want to be at 9 on this one. Lower the better. 255 on the amps. This one is flat. Really doesn't make any difference. This one, well, we want to be at 2 there. Now all we have to do is dial those into the process. Dial those settings in and let's see what happened. And that's exactly what we did. Look at the spatter. Can you see any spatter at all? Perfect. A perfect weld. There was 480,000 combinations. We did 12 tests, and from 12 tests we found out this is so much faster, so much better than skill. No other technique beats this. DOE. It's the fastest way to find out. Now, of course, we can go back to lean type tools and we can start putting visual signals on some of our settings here. Now we're doing TPM type work, we're doing lean type work, we're doing visual management type work. So we started off with the value stream map. Then we went to Six Sigma, did some DMAIC. Now we're back doing TPM. What a great example of Lean Six Sigma. That is the way these tools work together. They are the most fantastic techniques. And if you want to do this, if you want to save loads of money, and if you want your processes to be running at the absolute best settings, this is the only way to do it. Lean and Six Sigma. Give me a call and I'll show you how to do this.
Well, I hope you found that useful. If you've got any questions about that topic, or indeed anything to do with Six Sigma or Lean for that matter, give me a call and I hope to hear from you soon.